Here we are given the graph of polynomial function f of x, and we want to draw a graph that represents the rate of change in f of x. We have some rules we will follow, and of course we will start with number 1. Where a tangent line has a slope of 0 becomes an x-intercept. The tangent line is 0 at these 3 locations: at this maximum, and this minimum. So let's move each maximum and the minimum vertically to the x-axis. It's always good to know where a function hits the x-axis. Now let's look at rules 2 and 3 simultaneously. Let's start with rule 3. An increasing interval on f of x becomes a positive interval on the rate of change function. Note that both intervals start at negative infinity and end with the same x-coordinate. Rule 2 says that a decreasing interval on f of x becomes a negative interval on the rate of change function, but there are 2 x-intercepts on this interval for the rate of change function, so the rate of change function has to come down to a minimum and then back up to the x-axis. Both intervals begin with the same x-coordinate and end with the same x-coordinate. Let's go back to rule 3, which says an increasing interval on f of x becomes a positive interval on the rate of change function, but this interval must begin with an x-intercept and end with an x-intercept. So the rate of change function will come up to a maximum and return to the x-axis. Both intervals begin with the same x-coordinate and end with the same x-coordinate. Let's go back to rule 2, which says a decreasing interval on f of x corresponds to a negative interval on the rate of change function. And since there is no other x-intercept for it to return to, it continues to the right forever. Both intervals begin with the same x-coordinate and extend to the right forever. So we were able to draw the rate of change function with just 3 rules, but let's make sure the other rules check out. Let's look at rules 4 and 5. Rule 4 says a concave up interval on f of x corresponds to an increasing interval on the rate of change function. Let's note that each interval begins with the same x-coordinate and they end with the same x-coordinate. Rule 5 says that a concave down interval on f of x corresponds to a decreasing interval on the rate of change function. Each interval begins at negative infinity and ends with the same x-coordinate. There is another concave interval here on f of x, and it corresponds to this decreasing interval on the rate of change function. Both intervals begin with the same x-coordinate, and both intervals extend to the right to infinity. Rule 6 says an inflection point on f of x becomes a minimum or maximum on the rate of change function. There is an inflection point here on f of x, and there is an inflection point here on f of x. This inflection point moves vertically to the maximum on the rate of change function. This inflection point on f of x also moves vertically to the minimum on the rate of change function. So rule 6 checks out. Rule 7 says a linear interval becomes a constant interval, but we do not have any linear intervals. Rule 8 says a constant interval becomes a zero interval, but we do not have any constant intervals either. So in this function, all the rules checked out, and we feel really good about what we have drawn.